starting our late afternoon session, and the first talk by Alexey Litvinov from Skoltia in Moscow on correlation numbers in Virasoro Minimal String Theory.
Okay, thanks a lot for introduction and welcome everybody. Good afternoon. I should say it's a great honor for me to participate in this conference. I think last time I participated in a conference named Baxter was 10 years ago in Palmkov, if I'm correctly spelling the name. And unfortunately, that was the last time I seen live Rodney Baxter and also Ludwig Dmitrich Fadeev. And I should say that even without such these founders of the field, which we are doing, we still have to find will and bravery to continue doing mathematical physics in this rapidly changing world. So my talk is based on a forthcoming paper, which is done in collaboration with my student Dima Fromov. The paper is ready, 99% ready, and will appear very soon in arXiv. So let me briefly introduce you to the subject, what we are doing. So we're studying, we're working in the field of non-critical string theory. So what I mean by this, so formally, you should think of it as a formal action. So it's a direct sum of three theories, basically. You pick some conformal field theory on your choice. Then there's another conformal field theory called Liouville theory. And there's also BC Gauss, such that the total central charge is equal to 0. And this is how these theories communicate with each other. You are interested in this theory, you're interested, the observables which you're interested in correspond to heuristic homologies. And the simplest class of observables, we denote them as U. Sometimes they call tachyonic operators. And they obtained as follows. You pick some primary field from your CFT. So I denote it by phi. It possesses some conformal dimension delta. And then you dress it by some Liouville primary field, such that the total dimension is 1, basically 1, 1, left dimension is 1, right dimension 1. So that's how you produce a one form, and this one form can be integrated. So, and the goal is kind of in any string theory is to compute the amplitudes, correlation numbers. So basically, they will be denoted by V of G and M. G stands for genus of the corresponding Riemann surface, and corresponds to the number of insertion points where your tachyonic operators live. Sometimes you need to multiply your correlation function by the Gauss contribution, and then you integrate the whole thing over the modular space of curves of genus G with n mark points. So this amplitude, this set of amplitudes, is the primary interest in this theory. The most well-known example, probably most of you know, is the so-called minimal string theory. It is also known under the name minimal Liouville gravity. So in this theory corresponds to very specific choice of the meta CFT. It's basically pick a single minimal model CFT. And so this theory was studied a lot, and probably the most well-known fact about it is that it's believed to be dual to the double scaling limit of certain matrix models. And I should say that most of the results corresponding to this minimal string theory have been obtained on that conjectural dual side coming from the matrix models. But today I will be concentrated on another model of quantum gravity, or non-critical string theory, better to say. It was proposed recently in this paper by Kalieber, Hartmann, and Rodriguez was named, it's kind of strange name, the Virasoro Minimal String. And I will explain in some details what it is. And the conceptual difference compared to the minimal string theory is that the spectrum of underlying conformal field theory is continuous. And having something continuous is always an advantage because you can use like analytic arguments to compute things. And this is exactly what I'll be doing today. And moreover, in that paper, very nice paper, they conjectured closed formula for all the volume and all the amplitudes for any genus and any number of essential points. In particular, they claim that these amplitudes are polynomials in deltas in dimensions. In particular, the 4-point volume on a sphere is given by this simple formula. It's just a polynomial, quadratic polynomial in the momenta of the corresponding Liouville primary fields. So my goal today is to prove this formula. As you will see, there are still some loose ends in my proof, but conceptually I understand how to prove it. So I'll start briefly with the introduction both actors in this theory. So as I mentioned, so let me show again. So any non-critical string theory consists of some particular CFT, Liouville theory, and also ghosts. So right now I will be explaining these two terms here in this action. So I call it Liouville CFT. So basically I will use bootstrap approach. I will not use any action and formulate everything using the conformal bootstrap approach. So Liouville field theory is a conformal field theory. It has a central charge, which is usually parameterized by the parameter b, as here. And today I will treat b as a complex number, but in fact, I will be interested primarily in either real or imaginary values of p. Yeah, so this theory possesses the Virasoro algebra, basically the two copies of Virasoro algebra, these commutation relations, and I will need the notion of the primary fields, which are very well known. They're killed by positive part of Virasoro algebra. They are eigen states for the operator L naught, and they have the conformal dimension, which I will parameterize by the moment as follows. So P here, I will define everything for P line on a real line, and then we'll continue analytically away from this region. So as you might see, the dimension enjoys this symmetry, and that's why usually, that's why we demand that the two fields which differ by the change of sign of momenta are the same, and up to some coefficient proportionality of up to some reflection amplitude. You also know that the conformal bootstrap basically requires you to know-link the 2 and 3-point functions. In some sense, 2-point functions are a matter of your choice of normalization, but 3-point functions are non-trivial dynamical quantities which are not fixed by conformal symmetry, and you have to deduce them from some equations. So how we do it usually, we consider the condition of associativity of operator product expansion. So in Liouville theory, I will postulate that once you expand two primary fields, then you have to expand it in a spectrum. So the spectrum is continuous, and what is written here, you integrate over a real line over the spectrum with this structure constant. This is the standard factor here, and also you sum over all descendants. So the summation, the descendants are labeled by partitions, by basically pair of partitions, because you have two Virasoro algebras. And what is important, that all the coefficients beta here I kind of absorbed them in front of the structure constant. All these coefficient beta are completely fixed by conformal symmetry. The only fact which I'll be using is that they are, of course, they're rational functions of the momenta, and they have poles in the momenta P, which sometime I will be calling internal momenta. They have poles that cuts values responding to this special values. Okay? So now another gradient which I will need, I will postulate the existence of degenerate fields. So somehow I will treat degenerate fields as a separate set of fields, not necessarily related to the previous ones. So I postulate that there exist fields which have precisely these momenta. So better to say they are parameterized, the dimensions are parameterized by the momenta. But as we can hear, they do not lie in the spectrum in general. So that's why they are different. And I will demand that the corresponding null vector, since this field corresponds to Katz fields, the corresponding null vector vanishes. So basically, this, as for example, is in minimal models of conformal field theory, all the null vectors are set to 0. Because of this vanishing condition, correlation function with degenerate fields obey Beeline polynomial differential equations, and it puts constraints on the OPE of this field, of degenerate field with arbitrary field. This is well known. And so another reminder, so in order to derive three-point function for arbitrary fields, not degenerate, it's enough to consider the following two 4-point functions. So you consider 4-point function with one degenerate field and 3 arbitrary. You see they kind of have different notation. So for arbitrary field, I'm writing the momenta here, but for the degenerate field, just two integers here, positive integers, and they're not necessarily equal. But once you demand the single valuedness of these two relation functions, they are expressed as the solutions of hypergeometric equation. You can compute everything, and the condition of single valuedness will be equivalent to the following two sets of functional relations. And it should be stressed. So this functional relation, this is a kind of shift relation. You have a symmetric function of 3 variables, the structure constant, the 3-point function. And it is written here, but once you shift it either along by B or B inverse, and so this ratio is very explicit, ratio of the gamma function, small gamma functions. And it should be, I should remind that you can convince yourself that for real B and for purely imaginary B, these two equations have a unique solution. Unique once the normalization of fields is chosen. Okay. So the first solution corresponds to real B. It's called space-like Liouville, or this is the ordinary Liouville, which you're probably familiar with. So the 3-point function is given by this remarkable formula. So the key ingredient here is the so-called Upsilon function. It admits an integral representation, but what is important is that to list all the poles and zeros of this function, of the 3-point function. So basically, the poles are located at what I will call later the screening condition. So basically, the sum, the arbitrary signs here of the momenta, of 3 momenta equal to the special Katz value. And also there are zeros at this point. So now, so having defined the OPE for real momenta, we might try to analytically continue them away from those points. So what's the problem basically here? So the integrand in the OPE, it's a meromorphic function of, say, let us fix P2 and analytically continue in P1. Then the integrand here, it's a meromorphic function. It has a lot of poles coming from the structure constant here and from the OPE coefficients as well. And once they move, sometimes they might pinch the contour, and you, in principle, might have a divergent turn here. You might have poles, but in fact, that's not going to happen. Concurrent analysis show that the pole which appear, for example, the pole which appear from the at the degenerate value of the momenta, it's cancelled somehow. It is cancelled by the zero coming from the 3-point function in such a way that you basically have this equation. So this equation is not trivial. It says that the degenerate fields which I postulated before, they basically are correspond. They are just limit of the analytical. They obtained as analytic continuation from the spectrum of the original primary fields on the theory. Yeah. So the details you can read in our paper, and it says that it also requires the so-called higher equations of motion discovered by Alexey Litvinov. So what it is, it's basically, in a sense, the next order in the expansion. In this equation, once you approach P to this degenerate value, so it states here. So in the leading order, you have the condition that the null vector vanishes. So you have this, and on the next order, while expanding, P goes to Pmn, you will have this equation. So it basically says that applying this null vector operator to the logarithmic type of operator, you will obtain primary field with which is not the degenerate, but because there is minus here, which corresponds by dimensional analysis is just the dimension of the corresponding null vector, which is 0 here, but here because you differentiated with P, you obtain these equations. And the proportionality coefficient here is explicitly null. All this can be derived just by complex analysis exercise precisely. Okay. Now another fact, quickly. So you can also prove that any multipoint correlation function. So here, sorry, I'm considering only the case of sphere, but it can be readily generalized for higher genuses as well. So if you study this function as a function of the external momenta, you can prove kind of by induction the only poles. Again, I fix P2, Pn, and consider it as a function of P1. The only poles are so-called screening poles. So I will not explain. So somehow these poles correspond to the sum with alternating signs P's, and the poles appear at these quantized values. Sorry, another ingredient, probably not very wide known, is called the triality symmetry. So it holds only for 4-point function on a sphere, and it can be proven that this function is invariant on this finite transformation. So instead of, so P, for example, P1 is sent to this half of sum of all momenta and other momenta sent to these values. And it can be proven, it's just kinematical fact, in fact, just this symmetry fact that everything which enters in the definition of correlation function, I mean, the structure constant and conformal blocks, they all enjoy the symmetry, and you have kind of this covariant type of equation. So you can transform by triality. Don't ask me why it is called triality. This name called it somehow comes from the AGT relation, but there is a slang which calls this triality transformation. Okay, now I move to time-like Liouville view. For time-like, I'm taking B being pure imaginary. Then, as I said, there is another unique solution of the functional relations, which is looks different because now it's kind of inverted. All the gamma function or epsilon function from the denominator here in the numerator and vice versa. Now, this three-point function has a bunch of zeros which appear at what we would call a screening condition, but the poles are only at external. The poles don't appear. The poles appear only at Katz values. So sorry, these are not Katz values. These are the values which correspond to known vectors. Okay, so it is conceptually different because the poles are now become zeros and vice versa. So here's a long text of what is written here. So in a sense, the OPE, the integral of a real line in time-like Liouville is ill-defined because on a quantum of integration, you have infinitely many poles. Moreover, it's not just infinitely many, but in a sense, it's very strange. They are dense on that line. So once you study the expansion of conformal blocks, at each order, if you truncate, at each order you will have finite, no, you will have infinitely many, but not dense set of poles. But once you sum over all contributions from the OPE, you will have densely filled line with poles. And in a sense, you can think of this line as being the natural bound of analyticity of this function, which you integrate. That's why it has been suggested to integrate slightly above, just shifting by a small amount above the real line. And this is, and you can check, probably prove that this is the correct definition in the sense that the associativity of the operator algebra will be satisfied. And because of this, because of two facts, first of all, that you are integrating above this strange bound of analyticity, and also because your structure constant has less kind of less poles than in space-like Liouville. The analytic structure of amplitudes in this time-like Liouville theory is much simpler. And namely, it has only poles at the Katz values of the external momenta, right? And doesn't have, sorry, but only external momenta correlation function. It doesn't have any screening condition poles. So important difference compared to space-like Liouville that the degenerate field, sorry, it's called degenerate field, but better to call it somehow else. So the field which is once you analytically continue to the degenerate to the Katz point, it has a non-vanishing null vector. So compared to space-like, the null vector doesn't vanish, but instead you have these high equations of motion. So acting on it by the special null vector operator, you obtain another primary field with dimension m minus n. Okay, now we come to the amplitudes. So basically, I just remind you, formally, Virasoro minimal string, exactly as was in the introduction. You have space-like Liouville. They should be swapped, basically. You have time-like Liouville for your matter, space-like Liouville, just ordinary Liouville, and for the of Gauss. You can check that the condition that the central charge is zero corresponds, it is translated to the equation that the two parameters of this theory are related as follows, and also the momenta of this. And then you multiply correlation function from Liouville, from time-like Liouville, from Gauss, and integrate over your surface. So the first non-trivial volume is a sphere with four punctures. And the modulus space which you integrate is just a position of one of them, because the other three can be fixed. Usual choice is 0, 1, and infinity, shown here. So practically what you do, you multiply two 4-point function and integrate them of the position of the first field, for example. It is important that because of this condition that the total dimension is 1, so you basically integrate in the one form. Some of the fields here, either in time-like or in space-like or in both, do not lie in the spectrum. So, for example, if you stick your Liouville fields line in the spectrum, then the matter fields necessarily will be not in the spectrum. So this volume, as it is from the beginning, assumes some kind of analytic continuation. And now let me mention an important thing. As I explained, all the correlation functions here are complicated meromorphic functions of the external momentum. They have poles in different values, but the answer is a polynomial. It means that the residue of the integrand are exact forms. And so this is exactly what we prove here. So, and I also have to say that I explained there are two kinds of poles, either degenerate fields, so of the form P1 equal to PMN, or discrete poles. You can show that these two guys are related by triality transformation. That's why I will be carrying on the first type of singularities. So my goal is to prove that these are exact forms, and after that, I will try to compute this formula, to derive this formula. So what basically happens once you approach the degenerate value? So then you approach the degenerate value, then in fact you are on the support of high equations of motion in time-like Liouville. So this is the last equality here up to a fact. And then the key observation, which can be easily proved, that under the correlation function, you can somehow integrate it by so the last equality can integrate by parts. So that means that the residue, which you consider, is basically a total derivative. So dd bar of, so h here is some very specific differential operator, but it acts on a covariant object. And so that's why you can basically prove that this form is integrated to 0, that there are no boundary issues here, everything behaves well, and so the residue term is cancelled. And then we consider the next order, non-vanishing order. After the pole, you have some non-vanishing contribution. I will denote it by sorry. We just consider the next order. So in the next order, you have two contributions. You either differentiate the first multiple in your the Koenig field or the second one. So this is defined as here. And so it says that in the first term, you can use higher equations of motion and integration by parts, and also some analysis of the exact terms. You can invert it in the following equation, that the difference of two volumes of with P equals PMN and P equals PM minus N is basically given by this integral. Sorry, I speed up. So we define this quantity, which is this difference. Now it's a symmetric function of three momenta because the first one is fixed. Moreover, it's a difference of volumes. Then basically explicit calculation shows that this function satisfies this nice relation. So it's related at PRS, and at PR minus S is basically the same. And then, assuming that our volume depends polynomially on external momenta, this constraint basically implies that it doesn't depend on the first argument, because the second quantity is in fact dense on the real line. So you can approach any value here. So thus we proved that the sorry, it should be we proved this relation, and then we proved it should be P1 here. We proved that the volume itself. Oh, no, it's a P2. So after all, from this argument, we proved that the volume satisfies this equation, and it means that it's basically a symmetric function of this form, where f is some polynomial. And on the other hand, we have a reality symmetry of the volume, which implies this equation, and the only solution, the only polynomial solution of this equation is satisfied by quadratic polynomial. As any quadratic symmetric, any quadratic polynomial has two, sorry, it's quadratic, but has two coefficients only. These two coefficients, C1 and C2, can be found by considering exact cases, which are known since this paper, Noflis, Fatiev, and others from 2009. So for special values of the moment, we can compute these volumes analytically. In a sense, in this case, the integrand can be computed exactly. And after all, it's just the integral over fundamental domain, d2 tau divided by imaginary tau squared. And you can obtain these two values. Evaluating them, you come up with exact volumes. This is kind of a short overview of what we were done. Now I come to my conclusions. Basically, instead of I will list like lose the ends and I will prove. First of all, I have to say that it's if we can straightforwardly generalize our results for case of genus 1 with one mark point. I will not provide details, but it's very straightforward. So what is bad? We don't have any proof of polynomial growth of our volumes. So we were unable to find any satisfactory explanation coming from the bootstrap why these volumes grow polynomially. The second issue is that the reality symmetry which I used is a very special property of for punctured sphere, as far as I know. And because of that, the generalization to higher genuses and higher M is problematic, because for me it's not clear how to prove that the singularity, the residues of correlation functions are exact forms. So for some residues you can do it because you can use higher equations of Moulton, but for the residues of the type of a screening condition, at the moment I don't see any option how to prove it, but believing in that the conjecture of this nice paper is true, that should exist a proof of this statement. So that's why the generalization of our proof of that formula is not it's not been done so far. And moreover, I should also say that we have checked numerically the formula for the volume P04, and it perfectly matches the exact formula. But for higher numbers, even for for 5 punctured sphere, the calculations become very complicated, and numerics so far diverges, and it's not clear at the moment. It's not fixed. I think nobody did this exercise so far. And the last two items here. So these volumes, they are polynomial, and they remind pretty much the Mirzakhani result on well-Peterson volumes of surfaces with geodesic boundaries. And in Mirzakhani paper, he not only presented these volumes, but he also derived the recursion formula, which allows you to compute them, computing some simple integrals. And the derivation of such formula from CFT would be very appreciated. And also the last item, also in the Mirzakhani paper, she was able to relate the volumes and basically the Weil-Peterson form to the certain cohomology classes on a moduli space of curves, and so it would be interesting to find such a. It basically such a relation has been conjectured in the paper of Eberhard and others, which I was referring in the introduction. But it would be nice to derive this relation starting from the conformal theory point of view. So now I'm done. Thank you very much, and please ask questions if any.